Electrochemistry, important notes for exam. What is electrochemistry? Electrochemistry is the branch of chemistry that deals with the relationship between electrical energy and chemical reactions. Simple meaning, chemical energy is converted to electrical energy or vice versa. Key concepts in electrochemistry. 1. Redox reactions. Redox equals reduction, oxidation. Oxidation, loss of electrons. Reduction, gain of electrons. These reactions occur simultaneously. 2. Electrochemical cells, devices that convert chemical energy into electrical energy. Two main types, galvanic cell, voltaic cell, spontaneous redox reaction, electricity produced. Electrolytic cell, electricity supplied, non-spontaneous reaction carried out. Texture, electrodes and their roles. Anode, oxidation occurs here, electrons are released. Cathode, reduction occurs here, electrons are gained. Mnemonic, anox and red cat, anode oxidation, reduction cathode. Example of a galvanic cell, Daniel's zinc electrode Zeton in SO4 solution and copper electrode Cu in CuSO4 solution connected by a salt bridge. Reaction, at an anode, ZnZn forward bias plus 2e minus minus. At cathode, Cu forward bias plus 2e minus Cu. Shall I continue with more topics like electrolytic resistance and resistivity? Shakramana 1. Resistance are opposition to flow of electric current. Formula, conductivity, resistance, and resistivity. Shakramana 1. Resistance are opposition to flow of electric current. Formula, R equals rho fractor A, where R equals resistance, ohm rho equals resistivity, L equals length of conductor M. Cross-sectional area, unit of resistance, ohm, unit of resistivity, dir, ohm meter, Natchako. 2. Conductance, G, reciprocal of resistance, here unit Siemens or mcho, Cn. 3. Conductivity, Q or K, reciprocal of resistivity, kappa relation with conductance, kappa L, A, unit, Siemens per meter. Mnemonic, resistance, conductivity, they are inversely related. Formulas to remember, quantity, formula, unit, and resistance R equals dot frac L, A, O, conductance G equal frac 1R, S, conductivity Q, kappa equals G, S where M, resistivity, O equal RM. Types of questions asked. Type 1, find conductivity, given length, area, resistance, or conductance. Use formula, if resistance is given, kappa equal frac 1 R L A. If conductance is given, G kappa G Type 2, compare conductivity of two solutions, same cell constant, given G1, G2. Formula, frac K1, KG1, G2. Type 3, dilution-based questions, given individual conductivity. Find net conductivity. Formula, K text frac K1 V1 plus K2 V2, where V equals volume and K equals conductivity. Now, molar conductance, and formula in centimeter units. Lambda m equal for 1,000 and p equals in 1,000. Kappa equals conductivity, S centimeters, m's molarity, mol per L. Unit S centimeter mol minno formula in m units. Formula m and crack kappa 1,000. Kappa in S m is in unit. SM for equivalent conductance, and formula EQ equals a frac 1,000 times kappa E kappa, N equals normality, unit Q EQ and as one. Formula in M units, units N, SM squared EQ nubnums end. Just replace M start with N ta to go from molar to equivalent conductance. Trend on increasing dilution property. Trend reases more freedom to move S-tivity, like kappa, decreases less ions per unit volume. Molar conductance increases more freedom to move, SP for weak electrolytes. Factors affecting conductance are 1, nature of electrolyte, strong electrolyte, fully ionized, high conductance, weak electrolyte, partially ionized, low conductance, HTs, OH-NENs, other ions based on mobility. 2, temperature. Temp, ion mobility, conductance. 3, dielectric constant of solvent. High dielectric constant, like water, reduces attraction between ions. For conductance. Formula 4, viscosity of solvent. Viscosity hinders ion movement. Conductance. 5, dilution. Weak electrolyte, degree of dissociation F increases. So molar conductance increases. Strong electrolyte already ionized, but ion interaction decreases. Conductance still increases. Degree of dissociation formula, text number of ions dissociated, text total moles taken, or frac lambda m queta infinity. Lambda m minus m equals molar conductance at given dilution. Lambda m squared equals molar conductance at infinite dilution. Kohlrausch's law of independent migration of ions. Statement: at infinite dilution, each ion contributes independently to the total conductance of the electrolyte. Lambda circ AB equals circ here core A plus what circ B. Where lambda of circ equals molar or equivalent conductance at infinite dilution. Lambda squared circ A equals contribution of cation. Conductance circ B equals contribution of anion. How to use Kohlrausch's law. Useful for calculating conductance of weak electrolytes whose conductance at infinite dilution can't be measured directly. So we use strong electrolytes that have common ions. At her example, CH3CH, we want to find lambda EQ greedy H3 COH equals. We use lambda EQ3 COH equals lambda HCH3 SONA plus HCl lambda EQ NaCl. Trick: add what you want, subtract what you don't want. Final answer format CH3COH equals X plus Y minus Z. Conversion between molar and equivalent conductance. Formula lambda M equals N times lambda EQ, where chart N equals N factor total charge of ions per formula unit. Example AlCl3 sta Al cube minus at standard N equals 3 phi. So lambda M AlCl3 equals 3 times molar conductance uses subscript. Molar conductance uses subscript. Equivalent conductance usually written as lambda cube without subscript. Dissociation constant Ka for weak electrolytes. Formula Ka equals frac C alpha squared 1 minus alpha, where C equals concentration mole per alpha lambda empty degree of dissociation. Shortcut trick to solve questions. If question gives values like if question EQ at CH3 so EQ HCl equals Y, lambda them EQ equals Z, then to EQ CH3 so H equal X plus Y minus Z. Trick: first calculate everything in equivalence, then convert to molar conductance using lambda M equals N times lambda EQ. Would you like a practice question on this with step mnemonic trick? Lika ganam al Zn Cr reactivity series of metals. Mnemonic trick. Lika ganam al Zn Cr Fe Skb Cu Hg Ag AUPT. Lika gana mala jenka dipa sanpi apani guppi, yani replacement reaction. A more reactive metal can displace a less reactive metal from its salt solution. Example, Zn plus QSO4, ZnSO4 plus Cu. Zinc displaces copper because Zn is more reactive than Q. SRP, standard reduction potential, from top to bottom, SRP increases. Top metals like LiKCa have low SRP, strong reducing agents. Bottom metals like AuPT have high SRP, strong oxidizing agents. Reducing power to give electrons higher at top of reactivity series. These metals easily get oxidized. Li strong reducing agents. Oxidized. Reducing power to give electrons higher at top of reactivity series. These metals easily get oxidized. LiKCa, NaMg, Al, Zn are strong reducing agents. Oxidized electrons higher at bottom of reactivity series. These elements get reduced easily. CQ, Hg, Ag, Au equals CHAP elements used in oxidizing reactions. Nonmetals reactivity order SRP mnemonic trick. I broke Kali's fake OCl-Cl. SRP increases from iodine to fluorine. Summary table: high, reducing agent oxidized, low, high, oxidizing agent reduced. Do you want me to make questions on this versus full cell? Salt bridge, IUPAC notation, voltaic cell. LUP converts chemical energy, electrical energy. Based on a spontaneous redox reaction, electrons flow through an external wire. Electric current is produced by this electron flow. Half cell versus full cell. Type description. Half cell, single electrode with its solution, e.g. Zn squared mice. Full cell, two half cells connected via salt bridge and external wire. Trick for galvanic cell LOAN, L left equals O excitation, A nodes negative. Then right equals reduction equals cathode positive. IUPAC notation for full cell, anode solution, cathode. Example, Daniel cell, text ZNS, ZN2 AQ plus CAQ, CUQ. Salt bridge, purpose, maintains electrical neutrality, avoids liquid junction potential, contains inert electrolytes, e.g. KCl, KNO3, should not react with electrodes or solutions, the cans. Both cations and anions present, both must have same mobility. Standard electrode potential, E3. SRP, standard reduction potential, tendency to gain electrons, SOP, standard oxidation potential, tendency to lose electrons, relationship text SOP equal mass SRP. Standard cell potential is cell. Formula using SRP, text E3 cell equal text RP text cathode, or using SOP, or using says SOP equals the text SCRPA anode text anode. Plus Daniel cell example. ZN quadbide, CU cell equal text RP text cathode, or using SOP, or using says SOP equals the text SCRPA anode text anode. Plus Daniel cell example. ZN quadbide, CU quadbide, CU. Zn gets oxidized, anode, Cu quadbide gets reduced, cathode. Sarpu q square, 2 plus minus Zn quer. From and code at 1, relation between Gibbs free energy and cell potential, delta G equals NFE, where now it's delta G, Gibbs free energy change, N equals number of electrons exchanged, N factor. F equals Faraday's constant equals 9 to the 16,500 C per mole, E electrode potential of the cell. Also, delta G equals delta G circ plus RTQ. Now, 2, Nernst equation, general form, E equals E ferc minus frac RT NF or using base 10 logarithm, E equals E thirc minus frac 2.03 RT NF log Q. Nernst equation at standard temperature, 25 degrees or 298 K. At 298 K, E equals E0591 log Q. You can round 0.0591 to 0.06 for quick calculations in MCQs. At 4, step-by-step method to solve. Step 1, identify the reaction. Break the redox reaction into oxidation and reduction half reactions. Step 2, find the N factor, number of electrons transferred in the balanced reaction. Step 3, calculate reaction quotient, Q. Q equals frac text stoich.coef. Exclude solids and liquids from Q. Step 4, apply the Nernst equation. Use E equals either circ minus frac 0.591 like hen log Q. Example problem, SEQ1M, Zn quadbise a 0.1 m plus CUS top given. Given equals circuit text cell equals 1.1 do rho V, N equals 2 U, Zn2 plus equals 0.1 m, Cu quitter plus equals 1.0 m. Step 1, Q equal frac Zn2 plus C equals frac 0.11 equals 0.1. Step 2, apply Nernst equation, E equals 1.10 frac 0.05912 log 0.1. E equals 1.10 minus 0.0591, 2. 1.10 plus 0.02955 equals 1.13 V. Hash EMF of a cell, electromotive force. R1. What is EMF of a cell? EMF is the voltage difference between the two electrodes of an electrochemical cell. It's an intensive property, which means it does not depend on the amount of substance, represented by E cell under standard conditions. 2. General formula to calculate EMF. If standard reduction potentials SRP are given, E circ text cell equals E circ cathode minus E circ anode. Cathode, where reduction happens, anode, where oxidation happens. 3. If standard oxidation potentials SOP plus cell equals SOP plus RP. 4. If no SRP or SOP values are directly given, but full reactions are given, then use this method. Then use this step-by-step method. 1. Write the redox half reactions. 2. Balance both half reactions. 3, assign n factor, number of electrons transferred. 4, use this rule, N1E1 plus N2E2 equals N1 plus N2E text cell. Then E text cell equal frac N1E1 plus N2E2, N1 plus N2. Note, if a reaction is reversed, the sign of EMF is inverted, multiply by -1. Important tips, don't add EMF directly unless n factors are same. Multiply each EMF by its respective n factor before combining. If they give a full redox reaction, find half reactions and apply the above formula. Cathode, SRP of anode, SRP given, use difference. SOP given, use SRP. Reactions only, use E text cell equals frac N1E1 plus N2E2 N1 plus N2. Reverse reaction, flip the sign. Would you like two standard hydrogen electrode? Sheet 1. What is He? A gas ion electrode and reference electrode defined by IUPAC, denoted as text H2G, 1 text atom, 1 M. For 2, important properties of ESH. Standard reduction potential SRP equals 0 V, standard oxidation potential SO0. It acts as a baseline to measure the electrode potential of other elements. 3. Role in electrochemical cells. SHE can act as anode, oxidation half cell, cathode, reduction half cell. 4. Why we use it? We never measure the absolute potential of a single electrode, but all potentials are measured relative to She. 5. How to use SHE to find electrode potential by step. 1. Connect the given electrode with SE in a galvanic cell. To choose, if the given electrode is anode, is undergoing oxidation, and She is cathode. If the given electrode is cathode, it is undergoing reduction, and She is anode. 3. Measure the EMF of the cell using a voltmeter. 4. Based on the configuration, the EMF gives you, if your element is anode, E to circ equals text EMF observed. If your element is cathode, equals plus emoji recap. SRP, SOP equals 0. Used as a reference electrode. Never find absolute, only measure with voltmeter. Assign polarity carefully. Would you like me to give you types of electrochemical cells? 1. Galvanic voltaic cell. Spontaneous reaction, negative Gibbs free energy, produces electricity, oxidation at anode, reduction at cathode. 2. Electrolytic cell, non-spontaneous reaction, delta G, 0 positive Gibbs free energy, requires external electricity, oxidation at anode, reduction at cathode, but polarity is opposite. Anode is positive, cathode is negative. How to determine oxidation and reduction during electrolysis of aqueous solution. Step 1. List all ions present from electrolyte salt, H minus, and OH agents from water, any acidic basic medium. Step 2. At the anode oxidation, priority of oxidation, discharge of anions, anion oxidized to notes. And halides are absent from water. I-men, I2, easily oxidized, most preferred. Br2, ClNan, Cl, Cl2, OHO2 plus H2O. If halides are absent, SO-cryamines, NO3 menstat, not oxidized, very stable, water is oxidized. Reaction if OH mens, ox 4 OH mens, right arrow, O2 plus 2H2O plus 4E mens, has step 3 at the cathode reduction. 10. By priority of reduction, discharge of cations, cation reduced to condition gas, Cu aging metal, higher reduction potential, preferred, H star, H2 gas. If metal ions are absent, H2 gas plus OH mens in neutral basic solution, Na K Al not reduced. Water is reduced instead. Reactions, acidic, 2H plus 2E right arrow H2, basic, 2H2O plus 2E right arrow H2 plus 2OH mens. Our step 4, use the electrochemical series. Always refer to the series to know. For oxidation anode, look for species lower in SRP, more negative equals easily oxidized. For reduction cathode, look for species higher in SRP, more positive is easily reduced. Tips to remember, INMS, BR, MENA, CL, and OH, SO4, and NESHFRIND, anode preference, AG, SMICE, CU, H, H2O, NA, cathode preference. Water steps in when no favorable ion is available. Electrolysis of brine is a common example. Cl- is oxidized, Cl2 gas, H2O is reduced, H2 gas. Electrorefining. Electropurification, also known as electrorefining, is a process used to purify metals using an electrolytic cell. Here's a breakdown of the process. Process overview. 1. Impure metal anode. The impure metal is used as the anode. During electrolysis, the impure metal dissolves into the solution and positive metal ions are formed. 2. Pure metal cathode. At the cathode, pure metal is deposited from the solution, leaving behind impurities. The pure metal slowly builds up on the cathode. Key points to remember: anode reaction oxidation. The impure metal dissolves as metal ions, text MS, text M, N plus, AQ plus, Ne ferric. Reduction. Metal ions are reduced and deposited onto the cathode, N plus AQ plus N next, M purification. The impurities either remain in the electrolyte solution or settle at the bottom of the electrolytic cell as an anode mud. Example, electrorefining of copper. Anode, impure copper, Cu. Cathode, pure copper, Cu. Electrolyte, copper sulfate solution, CuSO4. Cu by AQ plus 2E minors. Cathode, Cu by AQ plus 2E min CuS. Summer electropurification, electrorefining, is used to purify metals. The impure metal anode dissolves and pure metal is deposited on the cathode. Impurities are either left in solution or as sludge. Faraday's first law of electrolysis. The amount mass of substance deposited or liberated at an electrode is directly proportional to the quantity of electricity charge passed through the electrolyte. Formulas you must know. Pasteurle 1. Q equals IT. Q, charge in coulombs, C. I equals current in amperes, A. T equals time in seconds, S. Dotted 2, W equals ZQQ. W equals mass of the substance deposited, G. Z equals electrochemical equivalent. Q equals charge passed, 3. Z equals equivalent weight, 5 Faraday, F, where F equals 96500 C per mole tau. 4. W E cos I of T, the 9 to 6500 E. Equivalent weight, I equals current in ampere. T time in seconds. Shortcut for moles, number of moles N factor equals Q, or moles of frac Q NF frac IT NF. This formula helps find moles of gas evolved or moles of metal deposited at the electrode. Emoji notes to remember: WQ psi, more current or time equals more mass deposited. Q charge is just current over time. W equals econ IT 96500 Nunchfry. Use this to calculate deposited metal directly. F equals 6500 C per mole. 1 mole of electrons carries 96,500 coulombs. Moles QNF. Useful for gases and ions. # Faraday's second law of electrolysis. When the same quantity of electricity is passed through different electrolytes, the masses of substances deposited or liberated are directly proportional to their equivalent weights. Formula W equals frac E times I times T, 6500. W equals mass deposited, E equals equivalent weight, I equals current A, T equals time S. Condition: if current I's and time T are same, then charge Q tau is same. Frac W1 equal frac W2 E2 equal frac W3 E3. In terms of moles and N factor, text moles 1 times N1 equals text moles 2 times N2 equals moles 3 times N3. Emoji notes. Equal charge, equal electrons, mass, equivalent weight, E. Tar. Compare E for multiple substances. Shortcut. A battery, or cell, is basically a galvanic cell where chemical energy is converted into electrical energy through a redox reaction. For practical use, a battery should be lightweight, compact, have constant voltage. 1. Primary batteries non-rechargeable. Reaction occurs only once, cannot be reused. Example, dry cell, Leclanché cell. Dry cell, Leclanché cell, anode, zinc containers, N, cathode carbon rod, C, plus manganese dioxide, MnO2, electrolyte paste of NaHCl plus ZnCl2, voltage 1.5 volts. Reactions: Rano text Zn plus 2e square by it. Cathode text NO2 plus text 4 square plus e to by it RaMnO OH3. Note: NH3 forms complex with Zn cord by Zn NH3 4 squared 2 plus. Mercury cell used in watches, hearing aids, anode, ZnHg amalgam, cathode, HgO plus carbon, electrolyte, KOH plus ZNO paste, voltage 1.35 volts, very stable. Reactions, ZnHg plus 2 text 208 ZNOS text H2O plus 2 E squares. Cathode, HgO plus 2 E squamide right arrow text HgL plus 2 text AMNH squared. Overall reaction, ZnHg plus HgO right arrow text HgL. Note primary batteries can't be reused. Dry cell voltage 1.5 volts used in clocks and remotes. Mercury cell has stable voltage 1.35 volts, perfect for delicate with key concepts, reactions, and high. Secondary cells, rechargeable batteries. A secondary cell can be recharged by passing current in the opposite direction. These are used in automobiles, power backups. 1. Lead storage battery, car battery, lead, Pb, cathode lead dioxide, PbO2, electrolyte 38%, H2SO sulfuric acid, voltage, ball of 2 volts per cell, 6 cells equal 12 volt battery, discharging reaction, battery in use, anode text PbS, plexo 4 square 2 mis AQ, right arrow PbSO4 S2E, cathode, text PbO square 2 S text so 4 AQ, 4 square H squared plus 2E square right S2 text A2O. Overall reaction, text Pb, plexed PbO2 plus 2 text A2 text SO4, right arrow 2 text PbSO4 plus 2 H2O. Charging reaction, the above reaction is reverse of 4 at both electrodes is converted back to Pb at anode, PbO2 at cathode. 2 nickel cadmium cell, NiCd cell, anode, cadmium Cd, cathode, nickel 3 hydroxide, NiOH3 electrolyte, usually KOH, longer life, but more expensive than lead acid. Discharging reaction, text CDS2 text NiOH sto 3 2 tests plus 2S2 plus 820. Summary, cell type rechargeable, anode, cathode, notes. Notes ahead, lead storage, yes. Pb, PbO2, 2, 2 verter, used in cars and inverters. Nickel cadmium NiCd, yes. CD, NeOH3, twice 1.2, long life, costly, efficient power. Fuel cells are a type of galvanic cell that continuously receive reactants, continuously remove products, directly convert chemical energy of fuels into electrical energy. Drawback of thermal plants, inefficient, 40% efficiency, polluting, uses coal, oil, gas, converts heat, steam, turbine, electricity, indirect, and lossy. Fuel cells versus thermal plants feature fuel cell thermal plant, energy conversion, direct chemical to electric, chemical, thermal, electric. Efficiency, 70-cent plan, 40-cent. Pollution, none, only water. High, CO2, SO2, NOCs, etc. Fuel used, hydrogen, methanol, etc. Coal, gas, oil. Sustainability, high, low. Now, hydrogen oxygen fuel cell used in Apollo space program, electrolyte concentrated NaOH, electrodes, porous carbon with PT-PD catalyst. Cathode reduction, text O2 plus 2 text H2 plus 4 E squared, right arrow forced, OH squared. Anode, I'll text 2, H2 plus text 4, right arrow forward, H2 2 plus 4. Overall reaction, 2 text 2 plus text O2, text H2, and a Shahab. Why fuel cells are awesome, eco-friendly, no harmful gases, highly efficient, portable, and scalable. Used in spacecrafts, experimental cars, backup power systems. Legend, a silent destroyer. Corrosion is the gradual degradation of metals due to their reaction with air, water, and chemicals in the environment. Examples, iron, rusting, silver, tarnishing, copper, bronze, green coating. Why it matters, destroys bridges, buildings, ships, tools, cost. Crores of rupees lost annually can cause accidents like bridge collapses. Chemistry of corrosion, rusting of iron. It is an electrochemical process, anode reaction, oxidation. Iron loses electrons, 2 FeS, right arrow 2 Fe2 plus 4 E square. E degrees equals -0.44 V. Cathode reaction, reduction. Oxygen gains electrons in presence of acid from H2CO3 O2G plus 4H squared plus AQ 4E squared arrow 2H2OL E degrees equals plus 1.23 volts. Overall reaction 2FES plus O2G plus 4H to square H2A2 plus. How to prevent corrosion. 1. Paint coating. Paint or coat metal to stop contact with air water. Greasing, oiling prevents moisture contact, common for machinery. 3. Electroplating. Cover with non-corrosive metals like tin SN or zinc ZN. 4. Sacrificial protection. Attach more reactive metals like Mg or Zine to the object. These corrode instead and protect the iron. Quick facts. Rust equals hydrated ferric oxide, Fe2O3 di-XH2O, moisture plus CO2 equals acidic water, H2CO3. Corrosion is a redox process, loss and gain of electrons.